So hi everyone, it is now 2200 UTC. So let's get started with the third session for Amaldi15, where we're going to be, it's going to be on, it's a focus session on pulsar timing. And the chair for this session is Ryan Shannon, who I will pass it over to you right now. So go ahead, Ryan Shannon.
Yeah, great. Thank you very much, everybody, for being here this morning, Australia time. My name is Ryan Shannon, and I'm on the faculty at Swinburne University in Melbourne, Australia. And yeah, we have a very exciting session this morning, where we go deeper into understanding pulsar timing array results and the pulsar timing array as a detector. So I'll remind people that there's a few different ways to ask questions. You can put questions in the chat, and it's also possible to do that anonymously. Also, if at the end of the talk you wish to ask a question verbally, please raise your hand and we are able to unmute you, and you can ask the question that way, and we can have a bit more interaction that way. So with that, I'll hand over to our first speaker, Jeff Hazboun from Oregon State University, who's going to give us an invited talk.
Thank you very much to the organizers of this session and the Amaldi meeting in general for inviting me to give a talk about calibrating a galactic-scale gravitational wave detector. I'm really excited to talk about this topic. It's near and dear to my heart. And this work that I'm going to speak about really involves hundreds of people around the globe, and I hope I do justice to giving everyone a sense of the immense amount of work that goes into this in PTAs around the world. I myself am a member of the Nanograv collaboration and of course the IPTA, and I am at Oregon State University. So the first thing I wanted to do was just flash up this sort of spectrum that we always show to folks about where PTAs live. And we are down in the nanohertz regime of our sensitivity. And one of the sort of bread and butter things that we talk about when thinking about detector characterization are these black lines that I'm showing, which show the noise of the detector. Some of you may be asking, but Jeff, my favorite detector isn't shown here. And more importantly, all of the richness of my detector and where it's sensitive are not shown in the space-based or the ground-based detectors. And to you, I say, why is that? If you're asking me why that is, that's a very good question. I wonder that at almost every conference I go to. And one of the things that I want to talk about today is sort of the richness that goes into the sensitivity curves and how much we really know about the noise in our detector. Now, you might think I have this chip on my shoulder about this, but really, I just have an agenda. And so I have these takeaways that I want everyone to walk away from this talk thinking about. And here's the list. I'm going to tell you everything I want you to know at the beginning, and hopefully I'll convince you of some of these things along the way. So one thing to know is that pulsar timing array, gravitational wave folks think about our pulsars as one end of the detector. Sometimes I get discussions about this, but that's the way we think about it, and that's the way we model it. And one big important thing is that we have no null signal channel like a lot of the other detectors do, at least when depending on what the signal you're thinking about. So for instance, if you're thinking about compact binary coalescences, you can really, there's sometimes when the signal's not in your detector. We don't have that. We don't have that ability. And so we really need to model all the things all the time. The timing model for the pulsar pulses, the gravitational wave signal, and the noise model can all be covariant and must be fit for at the same time. This is actually pretty similar to the LISA global fit and some of the challenges that we'll see when we start thinking about space-based detectors. And one, I think, again, really important point that I want to communicate to you is that there is this ongoing international effort to develop better noise models and at the same time deepen our understanding of neutron star physics and the interstellar medium. And again, PTA sensitivity curves are not just pi wedges. Hopefully you'll walk away with that. So pulsar timing arrays in 3 slides. I know that Sarah and Golem gave some plenaries earlier today, or depending on where you are yesterday. But just in case you weren't able to attend those and you haven't heard about pulsar timing arrays, we use pulsars as nature's clocks, and we think we really are looking at millisecond pulsars. And the idea here is that you have this emission off of the magnetic poles, and as the pulsar spins, we see these blips of radio, for us mostly, and it's those blips of radio that we think about as ticks of a clock. And we're really thinking about millisecond pulsars, so down in the left-hand corner here of this period versus period derivative. And the period derivative being really small is important because these are very, very stable spinning objects, right? They're so stable that we know the period of some of them to 15 decimal places, which is just absolutely extraordinary. And this is over a couple of decades of timing. We can be able to tell what the period of these pulsars are and predict the arrival of the pulses. And famously, in the history of gravitational waves, the Hulse-Taylor binary was observed for many years, and the cumulative shift of its periastron was sort of some of the first initial evidence that we were actually seeing gravitational wave emission from this binary. And famously, Taylor and Joel Weisberg published these results showing the general relativity prediction and the actual change in data with error bars that you can barely see here. So what we're doing is not just looking at one binary system, and those gravitational waves are not in our frequency range. We're actually looking for gravitational waves at much lower frequencies than those. And we're using the pulsars themselves and the timing to search for evidence of gravitational waves. This is the equation here, and here's some of the important points that I want to show you. There's this pulsar response function, and knowing the pulsar response function is really important. There's an Earth term and there's a pulsar term, because the pulsars are so far away from us, and there's, they can be 3,000 light years away. And so what's happening at the pulsar and what's happening at the Earth from a gravitational wave standpoint might be a little bit different. So we need to take both of those into account. And as the Earth and the pulsar are buffeted in the gravitational waves from some large nanohertz background, we see that in changes of the pulse arrival time here on Earth. They're either closer together or further apart than we expect, depending on how the space-time in between us is being affected. Okay, so that's the basics of pulsar timing. And now the basics of the stochastic background. So this is just showing one source. In the center here, this sort of spinning cloverleaf. If there was a gravitational wave at the center of the sky map, that's what it will look like in the residuals of in the strain of the pulsar. So every spot in the sky is if there was a different pulsar. The stars are just different examples shown on the bottom. These are just simple sinusoids that I'm showing here. And that's the effect that we look for over a single source. So here are 3 examples of single sources, but really what we think about the first signal that we have seen is the stochastic background, which is really the sum of many signals. So here I'm going to show the sum of 2 and then the sum of 3, and I'm going to add them up. The 3 that I'm showing at first are labeled on the bottom right here. And you can see at those low frequencies, there's many, many, many individual sources that go into any frequency bin. And it's the sum of those that we can see. There's a sort of order of magnitude between some of these low top individual sources and the actual power that we see. And so this is building the stochastic background. Here's 20 sources, and they follow, this famous power law that we expect if this is the power law, if it's only due to evolution from gravitational wave emission. And then I'll show you here, this is the stochastic, this is 200 sources. And of course, we're thinking about actually millions of sources at one time in our cosmic neighborhood, if in fact the background is due to the gravitational waves from supermassive binary black holes. Okay, so that's the really fast introduction to pulsar timing. And what I really want to get to is thinking about a timing array as a detector. And we have to take into account a lot of different things. Most of these millisecond pulsars are in binaries. That's sort of their evolution channel comes from being in a binary and getting spun up by a companion. We have to think about the interstellar medium. There's stochasticity in the emission mechanism of the pulsar. There might be spin instability in the pulsar. We have to think about where we are in the world and where we are compared to our solar system barycenter. We have to think about global clock standards and errors in atomic clocks and how we correct for all of those different things. So we really have a lot to think about when we're thinking about pulsar timing arrays as a detector. And one of my favorite things really is that everything about a pulsar timing array is astrophysics. The pulsar timing is astrophysics. The nanohertz gravitational waves is astrophysics. The PTA noise is astrophysics. And so a lot of my colleagues and myself sometimes, we think about the interstellar medium in this beautiful way and trying to understand what's between us and the pulsars. And for, a number of decades, people have used pulsars to sort of understand the interstellar medium, for instance, trying to figure out what's between us, mapping the density and things like that. From a gravitational wave standpoint, sometimes you might think about it in a different way. And so I kind of wear both hats, and depending on what we're trying to do, especially if we're trying to think about it as a detector, we might want to mitigate for this noise. And so this is a sort of schematic equation here about the pulsar timing model. There's this deterministic part of the timing model that the people who call themselves timers look at and try and understand. And so that's thinking about the solar system ephemeris, proper motion, binary motion, relativistic effects, which are really interesting and important for binaries that are really close together, evolving due to gravitational wave emission, things like that. White noise, so this is the really high frequency noise that's not correlated from epoch to epoch, thinking about template matching, the shape errors in our templates that we use to fit for the pulses, chromatic effects, usually due to the interstellar medium, pulse jitter, which is sort of intrinsic noise in the emission mechanism, radio frequency interference here on Earth. Chromatic noise, by chromatic, we mean things that are affected by radio frequencies. So this is dispersion measure and the variations due to changes in density of the interstellar medium, scattering delays due to the interstellar medium, frequency dependence of profiles for the pulsars. Profile changes are another thing that we think about as a source of noise. And then red noise, where red here means time correlated noise at really low frequencies. And of course, the gravitational wave background is one such thing, but there are other sources of this. So mismodeled chromatic noise can show up here. Intrinsic instability in the pulsar and the neutron star crust could show itself as red noise as well. And we really want to try and mitigate for as many of those things as possible when we're trying to use a pulsar timing array as a detector. I'm going to go through these slides really quickly, but just to show, there's often big questions about our white noise model because we have a number of white noise parameters. The sigmas here on the diagonal represent the noise error from fitting the templates to the pulses in the radio, but there are other effects we have to take into consideration, and this is the phenomenological models. The Fs and the Qs are just additional error we add because there are other effects usually due to, well, they can be due to radio frequency interference, or they can be due to jitter in the pulsars in the emission, or they can be due to other interstellar effects. They're not taken into account in that template matching error. So we need to add a little bit more there. And the J's are, again, this jitter or things that are correlated epoch to epoch and within an epoch, but not between epochs, sorry. And then those all get added up block diagonal wise. And again, I'm just going to show this really quickly, but this is in our paper. And we talk about connecting the physical model to this phenomenological model. So there's the column there that shows you where all of these different effects can show up in our phenomenological model and whether they're short or long-term effects. The long-term effects are important for the background. Short-term effects will be really important when we start thinking about single sources or other sorts of deterministic signals that are at higher frequencies. And of course, whether they're spatially correlated or not is also really important. And I know that Sarah Vigeland showed the slide of Katerina Taborzi's work on various spatially correlated errors. So I'm not going to talk too much about that here. This is the outline of the Nanograv 15-year detection characterization paper. These first few points are basically what I flew through in the last few slides, and I want to talk about the rest of this a little bit more in depth. But if you're looking for a in-depth introduction to noise in PTAs, I highly recommend this paper to try and understand some of these effects. So I'm going to talk about these last few points in the next few slides before I go on to sort of a survey of the work in PTAs around the globe. So in this paper, one of the things that we've done is a full spectral and noise analysis of the pulsars. what you're looking at here is a Bayesian spectrogram. We don't have the spectral resolution that one would have in a ground-based detector. So we can go to higher frequencies here, but especially when you're looking for the background, we're just really looking at the lowest 30 frequencies. And in our gravitational wave searches, we only use the lowest 14 frequencies. The orange lines here are that Bayesian spectrogram, the orange violins are that Bayesian spectrogram. And basically how far, so these are just posteriors in a Bayesian analysis. And if the tail goes all the way down, that's not a significant detection. But if it doesn't go all the way down, if it's isolated away from zero, that's a significant detection of some noise at that frequency. And so that's the orange plots there. And then what we do is we want to compare this sort of free spectral model to the model we actually use, which is a white noise model, which is flat here. Of course, this is an amplitude spectral density, plus a red noise model, plus the common uncorrelated red noise. Here's what I'm showing, or the gravitational wave background. They're very similar in our analysis, so doesn't matter too much for this analysis. The red is the same for every pulsar. It's that common signal we're seeing across all of the pulsars. Some pulsars have very significant red noise individually that they keep. So this one has that. It's the green dotted line. You can see most of the total noise is actually in that individual red noise model. The gray dashed line here shows the white noise in this pulsar. Then we do this excess noise analysis and compare what it looks like if we do a free spectral analysis, another Bayesian spectrogram on top of that power law model. So it's a very simplified model that we use, and we're just checking here to see, well, do we get any significant detections at any of these frequencies when we use the power law? And the answer is no. But below there, it shows the Bayes factors for that excess noise. And basically at every frequency, we get no significant detection of noise just using the power law. And this is true basically across the board for all the pulsars. There's one that has a Bayes factor of 10 across all 67 pulsars we used in the gravitational wave analysis. We take those noise parameters and we fold them into a kind of idealized spectrogram here, spectral line here, which is basically the power spectral density of the residuals. The residuals are sort of what's left over after we subtract the timing model from our data and any other noise influences that we want to look at. And this is the space in residuals where our high frequency noise is actually flat, as it should be white noise. The dotted line is just if you look at the white noise. The orange line is showing you the timing model's effect on just the white noise. And I'll talk a little bit more about that in a couple of slides, but basically there's a spin down fit for the pulsars that we need to take into account, which pulls a quadratic out. That's basically a high pass filter. And then those spikes are from fits we do at 1 over a year and 2 over a year for position of the pulsar and parallax. When we take into account the actual gravitational wave background and the red noise, the background here shown in gray, then the power in the power of the residuals here is this blue line. So that's really in the end what it looks like. And the gravitational wave background, because there's an Earth term and a pulsar term, the Earth term is the thing that's correlated. The pulsar term is actually noise because it's not correlated across the pulsars. So it really does add to the red noise of these pulsars. So we have to take that into account. So now I'm going to show you sort of this is the anatomy of the characteristic strain curve, sensitivity curve for a pulsar. Here we folded in all of the information for every individual pulsar. This is just from one pulsar. This is all of the pulsars folded together. Here it's using a frequentist statistic we call the optimal statistic, but this is the cross correlation statistic for a background. And just all of the pieces. The low end really has to do with the observing time of each pulsar. The high end has to do with the data precision that we get. Then there's the sky position and parallax that we take into account. And in the middle there, we're actually affected very strongly by the gravitational wave background and other red noise. And this blue line here shows the 15-year stochastic background sensitivity. So that's our sensitivity curve from this data set. The black curve is a power law integrated curve. So this is a technique where you basically pick a power law and you say, well, what would the amplitude have to be for the signal to noise ratio to be 5? And you sort of do that for power laws across a different set of slopes. and then you can solve for what the amplitude would have to be to give you a SNR of 5. So what we're doing here is a little bit circular. We're using all the noise and the noise of the background, which is of course our recovery of what the background amplitude is. But when we fold all of that into our statistic, we get A-hats here from the statistic that are very, very comparable depending on the spectral index of the slope of the power law. They're very comparable to what we get into the actual detection analyses. So this is just a kind of back of the envelope sort of check to make sure that everything is consistent of what we're seeing. We'd never claim anything from this, but just to know that our noise model is looking correct. This is a plot that Sarah Vigeland also showed in her plenary from the 15-year detection gravitational wave analysis paper. And this shows what we get from an extinction curve from our null distribution for the analysis. And the blue line is our empirical distribution of the null curve. And what I think is really interesting to see here is both this green curve and this orange curve really depend on all of the noise that we're getting from the detector. Okay, so we have to know the noise model fairly correctly for there to be any amount of agreement between those two curves and the blue curve, which is a completely empirical way of getting the null distribution. The fact that these match so well is really a tribute to the fact that we understand the noise in our detector fairly well. And of course, we're looking at a log scale here, and there are differences and they are important for what our significance is. But if this wasn't in log scale, you would not be able to tell the difference between these two curves. So another thing that we show in the paper is an accounting of the red noise. So here, what's happening on the left and on the right is we're showing the pulsars that have significant red noise when we just run individual analyses of the pulsar, whether there's red noise or not. And all of the pulsars here have significant red noise in an individual run. The gray pulsars lose that significance. So we always do this search for red noise in the pulsar plus whatever the common signal is. And when we do that search for the common signal, basically all of the power from that pulsar goes into the common signal, which is shown in the blue curve on the left here, those blue contours. So all of the power from those gray pulsars has moved into the common signal. And then there are pulsars that still have some sort of noise that's intrinsic to their data set that's not common across the pulsar timing array. And we see them sort of, a lot of them grouped up in the -12 and about 1.5 range. And this is probably unmodeled or mismodeled chromatic effects from the interstellar medium, or maybe other effects. There's sort of two outliers in the middle there. And on the right's the table that shows the list of all of these. Okay, so that's sort of the results from the 15-year analysis. I encourage all of you to take a deeper look there if you're interested. And I just wanted to come back to this idea that while we are trying to model the noise in our detector, we also get astrophysics out of it, right? What's happening with the scattering and the dispersion between us and the pulsars tells us something about the interstellar medium. We are trying to use various tools to also help us measure the solar wind. And there's work, again, across the globe into this. I know that the Meartime folks are looking at this. Katerina Taborzi's group also looks at this as well, trying to understand the solar wind. And we're also using Gaussian processes to model, this has been done for a long time, but using Gaussian processes to model some of the more stochastic elements of this as well, like what's changing in the interstellar medium. And this pulsar 1713 plus 0747 is known for these various events that are happening that probably now are profile changes. So we're trying to understand if we can model those as well. And of course, you could think about this again in both ways. So just depending on what day you're trying to do the analysis depends on how you think about what's in between us and the pulsars. So just to flag a little bit of work that's happening on this, one thing that's been done is the profile change that was first seen by the FAST telescope in China and seen by groups around the world is this profile change that happened in 1713. and work that Ross Jennings from West Virginia University has done on this to try and understand what's happening. It's a chromatic thing, but it's not monotonic. So as you change in frequency, the residuals from the days of the event are all over the place. They're sort of smooth over frequency, and they are chromatic in that sense, but they're not monotonic. So we really have to kind of dig into this and understand this. And one way that Ross has done this is to look at principal component analysis of the shape of the profile and see how the different components change over time. So maybe trying to use this as a way to track these profiles and these events to both mitigate against noise that we don't want when we're looking for gravitational waves, but also to try and understand what's happening in the emission mechanism of this pulsar. One of the other interesting techniques that's been really getting a lot more attention recently is this technique of cyclic spectroscopy. This is a technique that's from signal engineering, where the fact that we have a periodic signal allows us to take advantage of the fact that there's side bands of our signal. And when you take that into account, on the left, this is a dynamic spectrum. So this is showing the intensity of the pulses from a pulsar over time. And the change over time is really showing you the scintillation that's happening because of the interstellar medium. And you can see that we can definitely resolve some of those changes on the left. But after we use this additional information from cyclic spectroscopy for this pulsar, we get a lot more finer resolution of those scintilles and understanding of what's happening between us and the pulsar. So being able to squeeze more out of our data using this processing technique, which is really, really going to be important as we move forward with the telescopes that we have. And Stella Acker, so this is work by Jacob Turner, who's at West Virginia University, and he's been working really hard to implement this at Green Bank. And then if you have a telescope like FAST, so Stella Acker and her collaborators at Cornell got some open skies time at the FAST telescope in China, and they have phenomenal resolution and, of course, just phenomenal sensitivity. And this is preliminary work by Stella, soon to be out, showing again this dynamic spectrum on the left, and then the Fourier transform of this, which shows structure in what's happening in those scintilles. And you see these parabolic arcs, and the curvature of those parabolic arcs actually tells you the distance to various scattering screens. So how far away screens are along the line of sight to a given pulsar and other attributes of those screens. So this is really, I like to refer to this as interstellar tomography. We're really taking slices of what's happening along the way, and this is work that Stella's building this 3D model, and the black are scattering screens along the lines of sight to various pulsars in different directions. And here we're showing things like the local bubble and other molecular clouds and other shells that are known. And so we can really use the pulsars to map out where there are overdensities in the interstellar medium in our local area. There's been so that's some work that's been done in nanograv, and of course there's work being done again around the globe, and that was with FAST. And I've seen other preliminary results from the actual FAST team looking at some similar results, which look really, really awesome. Again, this is a global effort, and I want to talk now and switch over to the chromatic noise modeling that we're using in our time series for PTAs. And so I'm just going to run through these really quick, basically as quick advertisements for talks that are going to happen later. So Andrew Zick is going to talk about the Parkes Pulsar Timing Array efforts. And I'd say the Parkes Pulsar Timing Array, they were the first ones really to publish a paper about thinking about model selection for models for the different pulsars. And this is really important. In this work, they've shown some really interesting checks for Gaussianity and time correlations in the sort of residuals that they get after they use all their timing models, trying to get us closer to what it means to say we have the right model for a given pulsar. So on the left are their chromatic red noise parameters, and on the right, they're showing the changes that you get from using the basic versus the advanced noise models. And so that's in session 03B, if that's something that you're interested in. Later in this session, the Aman Srivastava is going to show results from the Indian PTA. And this is really awesome because they have like 3.5 years of data, but the really low frequency of the GMRT allows them to see a lot of these chromatic changes and a lot of these chromatic effects. I think one of the interesting results from their paper is that they're showing this extra chromatic process in this chi that you see on sort of in the center of the plot on the right. It's not where you would think it to be for scattering, which is supposed to be, that should be a 4 if it was scattering due to a uniform medium, supposed to be 4.4 if it was a Kolmogorov of turbulent medium, and it's much different from either of those. So there's something funny happening in this pulsar that's different from others, and these are really precise effects. They can measure these effects really precisely because they have these low radio frequencies where these chromatic effects are really important. And Aurélien Cholomot is going to show results where from the European pulsar timing array noise modeling, and I think this is really interesting, where they've folded in PTA data. That's their full plus data set. And you could see in the red noise amplitude and slope that they get a much better localization of parameters for this pulsar when they include that Indian PTA data, even though it's only the last 3.5 years of data for a pulsar that has, you know, a couple decades of data for it. So I think that's also a really interesting talk to go see if you're interested. And both of those are later in this session. Mir time is going to show some really nice results in session 06A1. So Matthew Miles is going to give that talk, and Matthew is going to actually show results for their search for the background. They're seeing a common process amongst their pulsars. They only have 4 years of data. So this is also true of the Chinese PTA with FAST. They're about at the 3.5-4 year mark, and they're also already seeing very good results for the background. So these very sensitive telescopes can get us there much faster, at least at the higher frequency regimes. Not sure what we'll be able to tell about the amplitude and spectral index without a few more years of data. But it's awesome to see this data, and it's going to get Mir time data is going to get folded into the IPTA data set, which is really, really exciting. And seeing the fact that this is an SKA precursor is just awesome, and really gets us excited for maybe the next generation, as long as we can get, of course, the observing time we need for these pulsars. And this is 1909, which is the golden child of PTAs here. This is after it's been corrected for all of the interstellar medium effects. It just has phenomenal RMS for this pulsar. And you can see this big wiggle in 1909, which is purportedly the red noise, which is going to be the background in a few years when they have a couple more years of data and can show correlations here. Wanted to take a step back and think about, so other PTAs have been using these Gaussian processes, chromatic models for a long time, and there's historical reasons for why they've used it. Nanograv has used a different model that we call DMX, but I just want to talk about, for both of those, for a long time, people only used DM, just the dispersion measured variations and changes, and didn't think about scattering because it's a subdominant effect. But I want to show how this what effect this has. So this is the time delay you get for some small change in the dispersion measure, and this is the change you get across frequencies. If I add a little bit of scattering to this, so now instead of being dependent on the radio frequency 1 over the radio frequency squared, it's dependent on 1 over the radio frequency to the 4th, then I get different delays. Okay, but on any given day, if I'm just trying to fit for the change in the DM on a given day, but I'm not trying to fit for scattering, well, I can fit this. So this tilde DM is just a different value of the DM, and you can see that it pretty much matches that line where I've injected a little bit of scattering on top of the regular just change in the DM. Okay, so you get these, you can fit for in a model both the DM and the scattering at the same time, and then that ends up adding a little bit of extra noise somewhere else, somewhere in the white noise model or some other place, and so that can change. Or the worst thing that can happen is they can go into the red noise. So this is one of the main reasons that we really think about adding these scattering models, which are done in all of these previous data sets. And we're just kind of starting this process. We've been starting it for the last few years in Nanograv. And Bjorn Larsson's poster is a really good place to look, where he compares the way that this is done. He compares the six pulsars that are done, that are observed in the EPTA and nanograv, and tries to use more EPTA-like noise models. And on the left is our DMX model and our E-core, one of our white noise models, and then the red noise that we get. And what I want to highlight here is this change in the red noise that we see when we include a chromatic Gaussian process. So this chromatic Gaussian process, this is scattering, so it's 1 over radio frequency of the fourth. You can see this kind of big, fairly significant dip in the chromatic GP at about the same time where we lose some of the little wiggle that happens in the red noise. And in fact, we know from preliminary studies I'll talk about in a little bit that we actually get better correlations when we use this chromatic model for 0613 minus 0200. So that's pretty interesting and great. And then, of course, whoop, that's a little offset for some reason, but those peaks are what I was trying to show, which is that as we start to peel away the onion here, we see this little blip here that appears in the chromatic and in the basis E-core. And there might be some chromatic event in this pulsar that we hadn't seen before that we've uncovered now. It might not be dependent on the sort of radio frequency dependence that we've shown before. So this is going to mean we have more looking into the data of this pulsar to go to. And these are preliminary full analyses for our 12.5-year data set that I just wanted to flash up here. So anyone familiar with the 12.5-year data set, that was the first time in nanograv that we detected a common process. The orange curve here is what we published and the results that we quoted in our abstract and things like that. That's a pretty steep spectral index. It only uses 5 frequencies because we were having these issues that the higher frequencies it only uses the lowest 5 frequencies. The higher frequencies seem to have some kind of noise that we couldn't ameliorate. Because if we included all 30, we got this green contour that's shown that has a much lower spectral index and higher amplitude. With using some of these more advanced noise models, we can use all 30 frequencies, and here we get something that's sort of in between those two results, but we're using all of the 30 frequencies. And if I compare a 30 frequency to 5 frequency analysis, then I get really cool results, which show basically that the 30 frequency and the 5 frequency results match. And of course, the 5 frequency results have a broader posterior, right? We have less information because we're using only 5 frequencies instead of 30. And this is exactly the kind of thing that we want, right? Is no matter the number of frequencies to not matter as much that we're using. So this is awesome. This is preliminary work that we're really excited about.
Yeah. You have about 5 minutes left.
Okay, thanks, Ryan. Great. So I'll just slow down here a little bit. And then just saying that all of this sort of going back to the full detector characterization and not just these individual noise models, but the full detector characterization of the detector allows us to sort of predict what our sensitivity will be into the future. And one thing that I'm really excited about is not only just predicting what our sensitivity will be, but being able to tune the detector specifically for looking for resolvable binaries. So now that we've basically have this really strong evidence for the background, now we ask, well, if the background is from supermassive binary black holes, then we should hopefully start be able to see resolvable binaries. And this is work that me and Javi Siemens and many other people did to start thinking about what we might see with the DSA 2000 telescope. This is a mid-sized project that will be in the Owens Valley in the next few years when it gets built. And this is 2,000 smaller dishes that are ambient. The receivers are at ambient temperature, and trying to understand what can happen if we use this telescope plus, so here green is mostly just green bank, and the telescopes that we've used projected to 2036. and comparing what our detection volume will be for these single resolvable sources, depending on various changes we can make. So one of the things that we lost when we lost Arecibo is our high cadence campaign. So for some of the pulsars, instead of observing them monthly, we observed them weekly, some of the best pulsars. And what we're showing here is that we gain a lot in high frequency sensitivity if we use, say, I think this is only just the best 4 pulsars, and this is a sky average sensitivity curve, just taking some time from the worst pulsars, putting it into the best pulsars in a high cadence campaign, increases our sensitivity and can really increase our detection volume. That's what I'm showing on the bottom right here. And so thinking about how we use the finite resources we have for telescope time, I think is a really important thing that we should be thinking about as we move into the detection era with pulsar timing arrays. And then just some advertisements for things that are coming soon. Thinking about the gravitational wave background as noise. This is already being done even in the 12.5-year single source paper for Nanograv, but other single source papers that are out right now from our 15-year analysis and other PTAs. We have to mitigate the background because the background's in the way of seeing these single sources. So we have to fit for both of those things at the same time. Again, we have this 12.5-year chromatic noise modeling methods paper on the way, and we're going to publish that soon. There are 15-year results that are sort of seasoned with these chromatic noise models. We tried it out on the single source search. The alternative polarization search is going to be out very soon, and we show that this is really important for 0613, the pulsar I was showing, and a couple other pulsars to include these chromatic models. And then we're going to basically redo the 12.5-year gravitational wave background search and the 15-year, hopefully, gravitational wave background search and see what we get and how the parameters change and maybe how our significance changes. We know from just changing a couple of pulsars out, we have very preliminary results that have been done by my grad student, Jeremy Baer at Oregon State, where we show a 250% increase in the Bayes factor just by subbing out a couple of pulsars, their noise, putting in better noise models for just a couple of the pulsars. So that's really, really encouraging. And we're really excited about what happens when we do the full model selection for these pulsar noise models and use it on the data sets. And so I do know how to include a full gravitational wave across the spectrum plot, just to show that to everyone. And just to say, this plot that's in the upper left hand here for Nanograv is available online. So there's a Zenodo archive. That's the QR. That's where the QR code will take you. It has sensitivity curves, the sensitivity curve for the for Nanograv 15-year data, and all of the individual pulsar spectra as well, if anyone's interested in that. So thank you very much, and I'm happy to take questions.
Thanks very, very much, Jeff, for the great overview. I guess if people have questions, if they could either ask them in the question box or put them in chat or raise their hand. Okay, I guess I'll ask the first question then. So a lot of our models are quite phenomenological in the sense that, you know, we assume that chromatic noise is frequency to the -4, for example, but that's sort of assuming a very idealized ISM. And I was wondering if you're curious as to like how much sort of misspecification of those models is impacting could impact the gravitational wave searches, or how much more astrophysics do we need to put in, or what to really get those models correct?
Yeah, I think that's a really good question, because when we search the index, whether it's supposed to be to the -4 or to the -4.4 or less, we seem to get different answers for different pulsars. One thing that's encouraging is we seem to get the same thing with different data sets from different PTAs, which is one thing I'm really excited about. So for instance, for the second dip, you and your compatriots found something in the one point something range for that second dip for 1713, and we find something similar in our 12.5-year data set. So I think that's really encouraging. I think allowing those indices of subdominant terms to vary is going to be really important in the near future, and trying to understand whether that's telling us something astrophysical or not. And I think that's something that, while I'm on the modeling side of things, I think we need expertise from folks from the ISM who understand the ISM, the interstellar medium, and the processes there about whether that should be expected or not. And another thing on that is that I'm really excited about the fact that people are sort of across the globe now, people are using a deterministic solar wind model. And one of the reasons for that is that the spikiness of the solar wind is not really well modeled by Gaussian processes. So you sort of need both to do that. But the cool thing there is that if you model the solar wind across all the pulsars, then you can model it out and maybe start to really understand that what you're seeing in different directions, what's left is really the ISM and not some mix of interplanetary medium and interstellar medium. So maybe we can start to use that to see, to tell us some more about what we should expect from the interstellar medium. I'm not sure which one will be more informative, which direction.
Great. Scott has a question.
Yeah, really nice talk, Jeff. So I had a question about like 1713, like events. As we're getting better and better data, better sampling, more sensitive telescopes and more MSPs, we're probably going to be seeing more and more of these event type things. And I was wondering if you have any thoughts about how we decide when and if we're going to need to add an event, even before we decide how we're going to model that event. Right, what becomes an event? And yeah, this was a great example with 0613, but is there any way, do you think we can do this rigorously?
That's a really good question. So one thing that, so this is in the weeds for 1 second, is that in in any data set where you have narrowband TOAs instead of something that's averaged per epoch, you need to include a white noise parameter called ECOR, and we can model that with a Gaussian process. And one thing that Bjorn actually figured out here is that when you can plot the Gaussian process of ECOR, and it's actually, because ECOR is telling you things that are correlated in a given day, it does show frequency dependent things. So you can see, for instance, the dips in 1713 when you plot this ECOR. And so I think that this might be a way that we can start to flag different epochs for something like a profile change. And so I don't know what exactly the metric would be, but something, looking at this top line on the right, I think there's something in there where we can show something, some change from the mean that allows us to flag a day or flag a few days for more investigation, right? And then you take this time series and then look at the actual raw data that we have from the folded TOAs.
Great, thanks.
Are there any other questions? I guess maybe I'll follow on from Scott then. And we've talked about doing wideband timing approaches, and I was wondering how these sort of profile events, and finding them and characterizing them will can be folded into those sort of wideband timing approaches, where you say have only a single TOA or a few TOAs across a wideband.
I think this is a really good question, Ryan. And honestly, it's something that I have that kind of keeps me awake at night a little bit, is that I really do think that it's important, and for a number of reasons, for us to start using wideband TOAs and across the globe, right? We're just getting so much data, and the data volume is sort of getting difficult to deal with. And of course, modeling things across these wideband receivers is also really important. I think that the methods that exist right now, they just don't have enough pliability to do the kind of searches that we need. And so I can imagine that maybe for a little while, we want to still have narrowband and wideband data sets, at least in the sort of near future. But I do think that there's a lot of potential there for a PhD project or a postdoc project, for someone to think about how we can incorporate more freedom into the wideband profiles and more frequency dependence. Maybe picking a basis that is generic enough to sort of look for different frequency dependencies, things like that. I've had conversations about this with people, and I'd love to have conversations with anyone who's interested in it, but I think there's a lot of potential there for good work.
Okay, is there any final question? Okay, let's thank Jeff again for the excellent overview of noise modeling and PTA detector characterization. And we now have a 10-minute break, and we'll be back in 10 minutes for Aurélien Charlemont, who's going to talk about the EPTA results. So we'll see everybody in 10 minutes. Okay, so we've hit the hour mark. So I will hand over now to Aurélien Charlemont, who's going to talk to us about noise modeling with a European pulsar timing array dataset. And I'll give you a warning at 3 minutes.
Hello, thanks. Okay, thanks. Try to put, okay, so I think everything is good. So thanks, Ryan, and thanks, Amaldi, the organizer, for letting me presenting you the results from the noise budget working group from the European Pulsar Timing Array collaboration. So here we present basically the result for the noise budget on the data release 2. Which consists of EPTA plus in-PTA dataset, which is it's basically a collaborative work that has been ongoing. And this was published, basically it was submitted last 29th of June in coordination with other papers from EPTA and other collaborations. And I think it's still not available in the ANA journal website, but you can still find it in the archive. And so the aim of this paper was basically to focus on the noise models of the EPTA datasets, as it was nicely presented by Jeff. Now it should be more clear for people who are not very very near to these works. So basically the aim of this paper is to produce noise models that we obtain from model selection that I will present later. And we also dedicate part of the work on the validation of these models. This will be the end of my presentation. So to give a broad overview of the framework in the EPTA that has been ongoing for the DR2, the data release 2. So basically the two first work modules, work module 1, work module 2, yielding to each work module to a paper basically. The first one was aiming at producing data from combining observations from different telescopes and applying the timing analysis. And so here I really focus on the single pulsar noise budgets. And so we basically perform iterative process to then provide data, so timing model and time of arrival, sorry. So basically a pulsar arrival time plus timing noise models, and sorry, plus noise models from our work. And basically these are used for any gravitational wave search. So the gravitational wave background that will be presented by Simon Chen later in the meeting. Continuous gravitational waves from a single source. And also a paper focusing on the implications of supermassive black hole binaries, dark matter, and early universe. The first one will be discussed by Alberto Cesana, and I think the last one, especially on the cosmic string, will be discussed by Hippolyte later in the meeting, and also a focus analysis on the ultralight dark matter. But also these works yielded by paper 1 and paper 2 is also being used by other working groups, such as working groups focusing on the interstellar medium. And part of this work will be presented by Francesco Iracis, also in the meeting. And sorry, also I didn't mention that Jiwoong later in this session will talk about works from the work module 1. Okay, so the EPTA data release 2 is made basically of different data sets, which could basically maybe confuse a bit, but we found that it was interesting to basically split in different time and data providers. So basically, we name these 4 data sets, the EPTA only data set, but that use only the new instruments, which basically observe pulsar with wider bandwidth, use more modern methods to compute to basically observe the data, and so which provides better quality data in terms of timing. The full data set, which also consists of previous data, and then you add a plus when you add on top of it, data from the Indian pulsar timing array, the first data release of the Indian pulsar timing array, which correspond of 10 pulsars. So basically, we add on 10 overlapping pulsars for these pulsars, and all the data set is made of 25 pulsars. So I will now discuss on the process and results for the noise modeling. As it was nicely shown by Jeff, we usually focus on different types of noise. So basically, white noise that is made of a few parameters, which basically model time uncorrelated signals. So basically, this is not represented in here in the plot, but it's basically just Gaussian noise in the data. And in the paper, we mainly focused on applying a model selection on the time correlated noise, which we also name red noise. That in our case is modeled as a power law, power spectral density, and we model them as Gaussian processes for all these 3 types that also have been presented by Jeff Hazboun. So the achromatic red noise, here I name it pulsar spin noise, but it could also have different origins that we name Rn here. DM variations, so it's variations that is usually stochastics, which is also basically a time correlated noise, but which depend on the observed radio frequency following this dependency. So basically 1 over the square of the observed radio frequency. And here I show an example of time varying DM in the timing residuals for simulated pulsars. You see that basically lower the observed radio frequency is, higher is the signal in amplitude. And scattering variation, which also could be related by the electron density inhomogeneities in the interstellar medium, that has a higher dependency in the radio frequency observed. And we also include deterministic signals, so such as exponential dips for this pulsar 1713 plus 0747 that was also mentioned by Jeff earlier. And also we include timing model errors, but that are marginalized during the analysis. So I won't be talking more about it during the presentation. So the method that we use, instead of applying a model selection on all the data at the same time, we basically follow a procedure to make it simpler. So we basically analyze each single pulsar individually. And for this, we use a set of candidate models, which are shown here. We use 5 different possible models. So red noise DM, red noise plus DM, DM plus scattering variation, and all the 3 together. We don't consider, we consider scattering variation only with DM, as we expect scattering variation to be dominated by DM, given previous knowledge. And another model is also included, which is only white noise in case of non-time correlated signal favored by the data. And basically, we apply a Bayesian model selection and get the most favored model. And another thing that we apply during this process is to basically fit for the number of Fourier modes that we use for the power laws. So we start for 1 over time span, and then we use a certain number up to which we stop the power law. And in this method, we fit for this number, as I will also mention later. which is also pretty nice for few pulsar, which are basically quite peculiar compared with others. And once you get the most favored noise model for each pulsar, we basically perform a parameter estimation for this pulsar, where we refit for the timing model. This time we don't marginalize over it, and then we get a posterior distribution for each of the parameters that are then used for the gravitational wave background or any gravitational wave search that we apply then for the other working groups. Okay, so this is just an example to show what type of posterior we get for this number of Fourier modes that we fit for. And you see that basically there is different behavior happening for different pulsars and parameters, which shows basically that there is basically quite complex spectrum in some cases that for which we need to focus a bit more. But basically this is what we get, and we just get a method to fit for it and basically allow the model to try disentangling the red noise regime compared with the white noise regime at higher frequencies. So for the results, we report that for main pulsar we get basically presence for DM variations favored by the data, but for which 12 and 21 are consistent with expected values of power law spectral index following Kolmogorov turbulence theories. And for the achromatic red noise, basically we find only that 11 pulsar are basically showing presence of this achromatic red noise, which is basically expected to consist of several noise accounting for the gravitational waves, and for which 6 of them are consistent with basically simplified gravitational wave spectral property from simplified population of supermassive black hole binaries. And so we also report peculiarly flat power laws for few pulsars for the DM variations, as well for the achromatic red noise. And this might show that we basically need to dig into more details at high frequencies. Certainly with the upcoming IPTA combined dataset, this will be also quite interesting to increase cadence and check at excess noise at high frequencies that could yield to flatter power laws that we measure. Okay.
3 minutes.
Then, sorry, how much?
3 minutes.
Okay, so I think I will have to go faster. So basically, some result by comparing data sets. For one pulsar, we have observed that we detect the presence of scattering variations and when we fit for this chromatic index, we fall to the right values expected for scattering variations, but including low frequency data from NPTA basically yield to non-presence of this signal. So basically, this will be also something to dedicate more time to understand for this pulsar 1700-3053. But it's also nice to see that EPTA only dataset was following scintillation measurements right nicely. Another thing that was shown by Jeff was the fact that including NPTA data yield to better constrain red noise in the posterior distributions. And then the final result point that I wanted to mention is for this pulsar 1713, one of the best time pulsars. When we cut the dataset in the first half of the full dataset, what we call tier 1, which was the data release 1 part, and the second half of the dataset, we are showing quite different spectral properties. The first one, higher spectral index, sorry, The second one more flatter power law. And when you have all the data sets, it's a solution that goes in between. And this will be also interesting to see when we combine from other PTAs to see if this could be something from happening because of our data set, or if this pulsar is basically also evolving around time. And then, yeah, maybe I will, it will be a bit fast, but I will try to mention the last point, which was validation analysis that we did for the paper, where we basically wanted to check that the posterior distribution that we obtain really represents the underlying probability distribution that we are searching, or if there is any bias in our recovery. And for this, you can basically produce PP plots from which you need to basically perform many simulations, run the analysis process for each of these simulations that basically are produced from different truth values. And for each of these true values, you see where they fall in the posterior distribution. You plot the cumulative distribution of this, and if your basically your model yield to proper posterior distribution, you go to this this diagonal line, and you can see how much at which sigma your posterior distribution vary from what you would expect for good results. And you can get basically for different type of bias, different type of shape for these PP plots. If this is too narrow, too broad, if this is shifted or not. And so we did it for one pulsar, this pulsar, 1600 again. And for this, we tried two type of simulation, red noise only, and all the candidate models that we used. And basically, we have seen something interesting, which is that when we simulate red noise, but not basically use the same cutoff for the low frequency, but go to lower frequencies, we see basically bias that is due to the fact that at high slope of red noise, you get basically biased values that shows that maybe maybe the unhomogenized cadence data or anything related with the data can yield to improper posterior distribution. And this behavior seemed to be removed when we simulate red noise with the periodic boundary conditions that are used for the models. And now we get basically a small bias from few percent from the red noise only, and also similar results from injecting red noise, DM variation, and scattering variations, which shows that basically we nicely recover what we inject in this case. But we think that this type of analysis might be also again thought to be used for the upcoming analysis. So I think I'm arriving to the end. I don't know how much time I left, and
if you can just conclude now.
I let it like this, I think.
Great.
Thanks.
Yeah, great. Thank you very much for the great talk. And so if people have any questions, if they could type them in the questions box or raise their hand, that would be great. Maybe if you just want to go back to your 1744 comparison, and I was wondering which model you think is correct and why.
So here, here we don't compare different models. We compare different data sets. So basically the bimodal distribution correspond to only ePTA, while the blue one is the same, but including in PTA. And you see that, you get, thanks to this certainly better characterization of DM variations, thanks to the low frequency low radio frequency data from in-PTA. This allows you to disentangle from potential leakage between red noise and DM variation models here. This is what we think, of course, but also we have cross-checked that this solution, I think it corresponds to more similar solutions than Nanograv, and I think we still need to compare with PPTA, but again, yeah, this is more cross-check to do here.
Great, yeah, we can take some discussion offline. Jeff, if you want to briefly ask your question, and maybe Aurélien can unshare his slides, we can get the next speaker up. So go ahead, Jeff.
Brilliant. I was just curious about the choosing for the number of frequencies, and if you find that there are a lot of pulsars that want a lot of frequencies and that slows down your analysis. Is that true, or are only a handful of pulsars really want a lot of frequencies?
So actually, the likelihood computation time, it seemed to not be much affected from what I have seen from the using. For the single pulsar noise models, from what I have seen, it was not highly impacted, at least with the ePTA data. I don't know with other PTA data set with more TOAs, maybe this could change. For the number of frequency bins favored, mainly for DM variation, it was favoring higher numbers than for achromatic red noise. For mainly all pulsars that show significant red noise, it was favoring low values, the lowest values that we tried. And yeah, few pulsars basically was showing high number of Fourier modes favored for the achromatic red noise, and these are the ones that we maybe might need to require more focus here. I think I'm still sure.
Yeah, great. Yeah, if you have more questions, please you can discuss it in the chat. And let's thank Aurélien again. And we'll hand over to the next speaker, Aman Srivastava, who's going to talk about the Indian PTA noise analysis.
Yeah, so hi everyone, I'm Aman Srivastava. I'm a PhD student at Indian Institute of Technology, Hyderabad, India. And on the behalf of Indian Pulsar Atomic Array Collaboration, along with our EPT colleagues, Aurélien, Gulam, and Co, I'll be presenting the work on the noise analysis of the MPIfR data release one. Okay, so let's have a brief overview on the MPIfR data release one. So it consists of 14 millisecond pulsars, and they were observed using UGMRT as a part of MPIfR experiment between 2018 to 2021. They have roughly a time span of 3.5 years, but it does vary for a few of the pulsars. Here we had the TOAs as well as the DMs obtained using two different techniques, that is the narrowband and the wideband technique. And for our analysis, we use the narrowband data set. So this is just a plot of TOA residuals, narrowband TOA residuals for all 14 pulsars. So through this plot, I wanted to emphasize you that if you look at all the pulsars on the left-hand side, such as 0437, 0613, 0751, etc., you can notice that along with the variations in the time span, as a few of them do not have a time span of 3.5 years, we also see that there are gaps between the data sets for many of these pulsars. And yeah, right. So in between 3.5 years of data set also, we have a lot of gaps, and also so let's have a quick overview on what noise models that we used. So for the white noise, we rescale TOA uncertainties using EFACs and EQuartz, and we know that EFAC gives us information about read emitted noise, and through EQuartz we can obtain the information about the pulse jitter in the data set. For the red noise, we modeled achromatic red noise and the chromatic red noise. For the achromatic red noise, we used the simple power law, and we fitted for the amplitude and the spectral index. And for the chromatic noise, we modeled DM variations and the scattering variations. Along with these two, we also we also try to find the optimum number of the Fourier coefficients for each and every pulsars. And in parallel, we also used a model called free chromatic noise model. In this model, along with fitting amplitude and the spectral index, we also fit for the chromatic index. So this model was used as a consistency check for the models that we obtained in our analysis to make sure that we have obtained the right model. And yeah, so let's say if we get a chromatic index 0, we infer that the chromatic red noise is dominating. If it's 2, we say DM variations, and if it's 4, we say scattering variations, and vice versa. For the methodology of the NPT noise analysis, so we use the narrowband data set for the current noise analysis work. That is majorly due to the fact that when we started the work, we actually did not we actually did not have the wideband data set for combined band 3 and band 5 data set, and so we were also interested in modeling the red noise as a Gaussian process, and in MPIfR file contained DMXs. So we had removed the DMXs and fitted for DM1, DM2 using tempo 2 in the initial step itself. Now, with a modest timeline of 3.5 years, there were a few pulsars which had the E-quartz unconstrained. So for the informity, we performed a Bayesian model selection for the E-quartz for each and every pulsars, and we found that few of those actually did not support the presence of E-quartz in their data set. And for E-quartz model selection, we set the base factor cutoff to be 10. Once we did the model selection for the E-quartz, we went along with we went for the Bayesian model selection among 6 pre-customized noise models, as you can see here in the table. So these are different combinations of white noise, achromatic red noise as RM, DM variations as DMV, and the scattering variations as SV. So we from the model selection, and we had set a cutoff of base factor of 100 or above to be one model to be preferred over the other. And in case of inconsistent base factors, we went along with the model with a fewer number of free parameters. Once we obtained what major noise models are present, we performed the number of Fourier mode selections, and these were chosen. The model selection was done using 4 predefined values for each pulsar. So as you remember in the TOA residual plot, you found that there are pulsars which did not have exactly 3.5 years of data set. So for each pulsar, these 4 predefined values were different based on their time spans, with the lowest one to be 1 upon twice the time span, and the highest coefficient corresponding to the maximum frequency of 1 over a month, that is twice the cadence of the pulsars. Once and finally, when we obtain all the optimum number of Fourier modes and the noise models, so we perform a parameter estimation for the final selected model. In parallel, we did a consistency check using free chromatic noise model, as I mentioned, where we fitted for the chromatic index as a free parameter to check whether we obtain the correct noise model. Right. So this is the final table for all the for the noise models for all the 14 pulsars. Now, when let's look at the red noise column. So you can see the spectral index for the for all the 8 pulsars where we were able to model red noise are very flat, apart from 1643. We think that is due to the small data span that we have, and we think that as we were not able to explore the lower frequency regime for the red noise to model its steepness correctly, so Yeah, so we found, so that is what we think is the explanation for the flatter spectral index. Now, thanks to the simultaneous multi-band low frequency observations of the UGMRT, we were able to model DF for 8 pulsars and scattering variations for the 4 pulsars in the data set. Yeah, so just like to emphasize on few of those results. The first of them being J1600 minus 053. So this pulsar actually showed in different PTAs such as EPTA the presence of chromatic as well, achromatic as well as chromatic red noise. But in our analysis using the Bayesian model selection procedure, we found there is none of the chromatic or achromatic red noises were preferred for this pulsar. So we performed a free chromatic noise model run, and we found, as you can see, the posterior, that the spectral and index and amplitude as well as the chromatic index are very much either one-sided and unconstrained, and we think that it is just modeling the white noise in our data set and shows the absence of any kind of red noise in the data set for this pulsar. And we see no such effect in the data set also. Now, in case of 1909, so for our data set, we found that the preferred model was red noise plus CM variations, but we had a significant base factor of around 85 for a model which has all the noise components, that is red noise, DM, as well as scattering variations. So we explored that using the free chromatic noise model. On the left-hand side, you see the posteriors, or a model where we model the achromatic red noise, and then we fitted for this free chromatic noise model, and we found that the chromatic index here, if you see, is has a median of 2.41, that is very close to 4, very close to 2. And saying that, yeah, so the data set has a DM variations, strong DM variations. On the right hand side, after we model the achromatic red noise as well as the DM variations, and then we fit for the free chromatic noise model, we find that that all the posteriors are bimodal or unconstrained. But if here the chromatic index, though it is the median, and of course the posterior is unconstrained, and we change the prior, the median would shift. But if you look at the maximum likelihood value, it was somewhere near to 2, showing that actually the part of DM variations was slightly getting mismodeled in the scattering variations. The noise, the power was leaking into that, and that might be appearing in the in the base factor values. We also did a visual check on the scattering effects on the 300 megahertz data set for the in GMRT data set for this pulsar, and we found no such effects, no scattering effects. And yeah, so that supported our claim here. And lastly,
you have about 2 minutes left, so if you could wrap up shortly, that would be quick.
Yeah, thanks a lot. Yeah. So yeah, so this is the last pulsar. So 1939 plus 2134. So for this pulsars, we were able to model achromatic red noise, DM, and scattering variations. But as we were doing this free chromatic noise model runs, so we did the same for this pulsar. But we found a peculiar thing here, and that was that even after modeling the red noise, DM, and scattering variations, if these were the DM variations, yeah, so and then we fitted for the free chromatic noise models, we found that that there is a residual noise even after getting even after these models. There is a residual noise with amplitude as log amplitude as -12.58, and chromatic index roughly peaking at 2.86. If we compare the amplitude with the conventional scattering model that we use, so the residual noise had the amplitude roughly 35 times larger than the conventional scattering model, and of course this spectral index was somewhere peaking at 2.86. So yeah, so we inferred from these results that here the chromatic index does not vary with the Kolmogorov turbulence with chromatic index of 4, and it might be one of those pulsars. And of course, we plan to investigate this further from direct measurements. Yeah, right. Yeah, so in summary, we performed the single pulsar noise analysis for 14 pulsars using PTA data. One data set, we found DM variations present in 8 pulsars, scattering in 4 pulsars. The results generally, the models broadly in agreement with the PTLs. There were inconsistencies, but we devote that to the short data span as well as huge gaps in data set. And of course, the future work for noise analysis using the wideband data set for the upcoming NPTA data release 2 is ongoing. Yeah, so yeah, thanks a lot. That is from my side. Yeah.
Great. Yeah, thank you very much, Aman, for your talk. So if people have questions, if they could raise their hands or type them in chat. Okay, maybe I'll ask a question. Scott, you can go first.
Yeah, great, thanks. Yeah, so I was wondering just about the future of the NPTA releases and stuff. Is the plan to continue to work basically one-on-one with the ePTA, or now that you have like substantial amount of data, are you going to try to make releases yourself? Has that been decided at all by the NPTA?
Well, I can comment on the upcoming data release. So we'll be adding roughly 2.5 years of data set more in the data release 2, and that will be an independent release. But yeah, so in the future part, I may not be able to comment as such.
Yeah, again, you noted that the chromatic index for 1937 plus 21 was shallower than frequency to -4. And there's lots of evidence for pulsars being shallower than -4 from scatter broadening measurements. And I was wondering if that had been measured for this pulsar. My Ramesh thoughts were.
Okay. For this pulsars, we actually did some literature survey. But in my knowledge, we could not confirm this, but there had been some studies for the scattering of these pulsars. And maybe if BCJ was here, he could confirm this, but we actually found that it is somewhere closer to this 2.8 value for this 1939. Yeah.
Awesome. Thanks.
Yeah, thank you very much.
Okay, if there are no further questions, we'll thank Aman again, and we can hand over to Jiwoong.
Hi, everyone. Nice to meet you. In this section, I will talk about the second data release from the European Pulse Timing Array. And I'm a speaker, Jiwoong Jang, and I'm a doctoral candidate at Max Planck Institute for Radio Astronomy. And this talk is based on the real publication submitted to ANA. In this case, I will mainly talk about the ePTA working module 1 about the dataset and timing analysis and update. And this project was led by Goram, Ko, and me. And I will start now. So in Europe, many universities and institutes are collaborating with each other under the European Pulse Timing Array to detect gravitational-wave and nanohertz. Recently, Indian PTA supported our work, and therefore we could publish our result. In this case, we are operating telescopes located each site in Europe. we are operating telescopes in two modes. One is single dish mode, provides high cadence, and the other one is simultaneous observing mode called LEAP. And this mode offers the high signal to noise ratio, and therefore they are complementary with each other. Another advantage of the EPTA dataset is that first, it has longer timing baseline, and second, its frequency coverage is very wide. Those are advantageous because first, longer timing baseline tends to improve Herling's curve signal to noise ratio, and also wider frequency coverage is beneficial to monitor and subtract the noise properties by interstellar medium. Thanks to the support of Indian PTA, our frequency coverage is even improved now. And based on the data set, we combined the data for 25 pulsars. We selected those pulsars because those can optimize Herling's curve signal to noise ratio, and those can cover uniform angular separation. It's important to constrain the Herling's curve as shown in this figure. And those pulsars were also analyzed in EPTA-DR1, and therefore in the following slides, I will compare the results we obtained in EPTA-DR1 with EPTA-DR2 with the EPTA-DR1. So to detect gravitational wave, we need data, and therefore data combination is essential. So to combine the data, we have followed the steps here for consistency. And first, we gather the data we have observed with different backends and telescopes. And then after the combined data initially, we checked the data visually in order to identify outliers and some features as summarized in this figure. And then we checked and removed the outliers. And finally, we conducted single pulsar noise timing analysis in order to update the timing solutions as well as extract noise properties simultaneously. And the figures here show our data set. The blue one is the data we added. We attached it into EPTA-DR1 data set. And compared to EPTA-DR1, the data length increased. Increased a lot. And we also could identify some structure before SPNT analysis, but they got removed after whitening. So in SPNT analysis, we run TempoNest in order to extract noise-free timing parameters as well as the noise properties. In this case, we collaborated a lot with Working Model 2 team, and we used customized noise models from EPTA Working Model 2. And then we conducted the basic noise analysis, and then we supported Working Model 3 to search for gravitational wave background signal. And this figure shows the example output of TempoNest. Basically, we updated the timing parameter based on the probability density distribution obtained from TempoNest, and then we measure the value based on the median, and then we also updated the uncertainty based on the 34.1% of each side of the Gaussian profile. And this is the example of the updated timing parameters. So in this case, we found new parameters in a specific timing solution for those pulsars. So basically, we found the new parameters for those pulsars newly in EPTA-DR2 compared to the EPTA-DR1. And thanks to such a new discovery of the new parameters, we conducted analysis on parallax annular orbital parallax, mass measurement, and binary orbital change, respectively. And I will explain one by one in the following slides. So first, I will talk about timing parallax. I will not explain what is parallax because we know already what is parallax. And based on parallax, we measure the distance. However, the initially measured parallax can be biased, so-called Rutschkecker bias. For instance, if we investigate larger volume, then there are more sources, and because of that, the dimmer sources tend to be underestimated in each distance. Overestimated in each distance, and brighter sources tend to be underestimated in each distance. Therefore, in order to get reliable distance, it is important to correct the bias, and we adopted the method suggested by Beovis et al. 2010, and then we reported the bias collected parallax in this table, and we compared the obtained parallax with the reference values obtained from VLBI, EPTA-DR1, and even pulsar scintillation. And we found that the measured parallax in EPTA-DR2 are consistent with the reference values. Moreover, we found some parallax signature for the first time, and we could not find any reference before. However, for those pulsars, the confidence level, the significance level is not above 3, and therefore, further research probably improves the significance level in the future. So, small summary is that compared to EPTA-DR1, in EPTA-DR2, we could measure timing parallax more preciser and for many sources. And then I will explain next annual orbital parallax. The parallax motion, in addition to the binary motion, changes the viewing angle, and because of that, the projected semi-major axis and the longitude of periastron changes over time. In this case, the inclination angle and ascending node angle are the important parameters to describe such effect, and therefore, in order to get the original orbital geometry, we conducted kin and com analysis. Kin is inclination angle and com is ascending node angle, and here is our result. For instance, in the left side, you can see the EPTA-DR1 result, and there was no preferred distribution. However, in the right side, you are able to see that the distribution here is more preferred, and in the future, the distribution will be more constrained. However, the point is that compared to EPTA-DR1, there is an overall improvement in kin and com distribution, and also we could find kin and com relations in EPTA-DR2, and they were not reported in the EPTA-DR1. So in EPTA-DR2, we could constrain the orbital geometry better than EPTA-DR1. And next, I will explain mass measurement. In this case, we used only Sharp delay. Please look at this figure. This shows pulsar and companion binary. When a companion is located at a superior conjunction, then the signal delay can be maximized. Sharp delay can be described by two parameters. One is range, depends on the companion mass, and the other one is shape, depends on the inclination angle. And if we know mass function, then we are also able to estimate the pulsar mass. And the basic way to analyze to determine the pulsar mass, inclination angle, and companion mass is using mass diagram. Please focus on this part. and you can see the intersection point between two Shapiro delay parameters. And by investigating this region, it is possible to constrain the pulsar mass, inclination angle, and companion mass, and also their uncertainty levels. So by adopting this technique, we could report the pulsar mass based on the Shapiro delay. However, for some pulsars, the tails are relatively long, and this is because of the huge degree of the correlation between two Shapiro delay parameters. And in the near future, we will include more post-Keplerian parameters in order to measure mass much preciser than now. And finally, we studied a binary orbital change. There are two contributions. One is intrinsic contribution due to gravitational wave emission, and the other one is extrinsic contribution by proper motion effect and galactic acceleration. However, what we are observing is the summation of the Earth effect and the obtained PV dot effect, sorry, the observed PV dot effect are described in this column. And in order to get the intrinsic PV dot, we subtracted the extrinsic contributions from the observed one, and they are described here. And then we compared this intrinsic PV dot with the PV dot, theoretically calculated PV dot. In this case, we used the mass from Shapiro delay analysis. And we found that most of them were consistent with each other, except some cases. For instance, J1640, probably because of the systematics. And finally, we determined the kinematic distance by assuming that only Skrabowski effect is remaining in the PV dot. This type of analysis is not unbiased, and therefore this can be a reliable measurement of the distance. And then we compared the kinematic distance with the parallax distance we obtained from parallax analysis. We found that most of them are consistent with each other, except some cases like 1022. And there could be some systematics, and therefore further research is needed in order to understand more preciser. So summary, here is a summary. So in EPTA-DR2, working module 1, our responsibility was data combination, and we updated timing solution for selected 25 pulsars. And then we also obtained the Bayesian noise properties. And based on the updated timing solutions, we measured those physical phenomena, and we found general improvements compared to EPTA-DR1. Thank you so much for your attention.
Great, thank you for the very interesting talk. And if there's questions, if you want to type them in the question and answer box. I've been told that you actually, participants can't use the chat. So sorry about that miscommunication. I guess maybe I was curious about the contribution of LEAP's data to the EPTA analysis, and what if there's been any assessment to like exactly how it's benefited the timing.
Sorry, would you please explain again?
So I was curious about the LEAP data.
Yeah.
And I was curious as to how, if there was some assessment to it.
Okay.
Yeah, if you could go into a bit more detail about how it's contributing to the EPTA analysis.
Okay, regularly we are conducting LEAP observation, and in this case, several telescopes are are operating simultaneously, and we process the data to combine the data set observed by different telescopes. In doing so, we can improve the signal-to-noise ratio, and because the signal-to-noise ratio is very bright, and therefore this can help us to obtain preciser timing compared to the single decimals, because of the signal-to-noise ratio. So even LEAP probably cannot provide high cadence of observation. However, the timing provided by LEAP can contribute greatly by providing very precise timing in this case. Yeah.
Okay. Are there any other questions for Jiwoong? Okay, maybe I'll ask another provocative question now that we're in a new sort of era in PTA gravitational-wave world, and is there what opportunities do we have as a community for coordinating efforts and dividing pulsars between different timing arrays, or tailoring our observations so that we have the best pulsars timed by the best observatories instead of everybody timing 909 to death?
Sorry, may I ask your question again? I think that I did not understand.
I guess maybe, yeah, it's a question as to should we think about do you have any thoughts about how to coordinate observations between different timing arrays? And maybe because we have a couple of minutes left, I know Jeff also had a bit on this in his plenary talk as well.
Okay. Maybe we need to discuss further in IPTA so that we can prioritize some pulsars. I think maybe we can collaborate with the IPTA. We are already collaborating with the IPTA, so we can communicate with each PTA. I think.
Cool. Anyways, I think it's it's worth us thinking about this a bit more, especially like with more sophisticated tools and thoughts that like people like Jeff have put together when we have better noise models about things. So with that, if there's no more questions, that concludes session 3A and my duties as chair. And I guess we'll hand over now to Junichi, who's going to chair the following section.
Yeah,
unless Scott has anything you want to add.
No.
2 minutes.
Yeah, I was just gonna thank you very much, Ryan, for that. I was just gonna introduce Junichi Yokoyama, who's going to be the chair of the next portion of this session. It's the last hour, but while we first start off with a 10-minute break, so we will begin the first talk in basically 11 minutes exactly from right now. So we'll see people back in a 10-minute break. All right, everyone, welcome back. The new chair for this last hour is Junichi Yokoyama. So go ahead, Junichi, go ahead.
Yeah, welcome to the last session of the day. Good morning from Tokyo. I'm Junichi Yokoyama, chairing this session. The first speaker of this session is Andrew Zick, and he's talking on the Nanohertz gravitational-wave background null hypothesis. Yeah, you have 15 minutes for presentation, so I'll give you a 3-minute warning.
Awesome. All right, thanks very much, and thanks very much for having me give this talk. So my name is Andrew Zick. I'm at CSIRO, and I'm here to talk about the Parkes Pulsar Timing Array, specifically about our advanced noise modeling as sort of the basis for our gravitational wave background searches. So some of the results I'm highlighting here today are across these 2 papers, which we published recently. and also from our data release paper, which I failed to include in the title slide. Okay, so for those who don't know, or might not have heard of the Parkes Pulsar Timing Array, we are a pulsar timing array that uses a 64-meter radio telescope, the Parkes 64-meter radio telescope, with its Wiradjuri name Jiwoong. We observe a set of about 35 millisecond pulsars in 48-hour blocks every 2 to 3 weeks, and we've been doing so since 2004. So we were the first formal pulsar timing array experiment, although there is legacy data that spans before 2004 for several groups. So the primary aim, of course, is to search for and study nanohertz frequency gravitational waves. In terms of the membership, it's largely based in Australia, and to first order, the people in the PPTA are the people on these two of our recent papers. So why do we do advanced noise modeling? Jeff gave a great overview earlier today. The unfortunate truth is that pulsar timing is sensitive to astrophysics. That's awesome if we're studying gravitational waves, but it also means that things like the interiors of neutron stars, the interstellar medium, the solar wind, our models of the solar system itself, and many other effects can induce signals in the times of arrival of pulsars. So because the gravitational wave background is manifests as a red noise process in the times of arrival of millisecond pulsars, we have to deal with all of these other effects that also manifest it as some as red noise processes, some as deterministic processes. So that's really our task. So the goal really is for any given pulsar, given it and its times of arrival, we want to fully characterize all signal present in those times of arrival. So, and the rationale is that before we describe the data under a gravitational wave background model, we try to do our best to describe the signals under a null model and have that null model that describes the signals present in the data. If we construct a poor null model, of course, we can that can lead to unreliable inference. So we really do our best to try and charge all stochastic and deterministic processes to particular bins before we do our gravitational wave background analyses. So some key points to consider when we're doing this. In a single millisecond pulsar, a steep spectrum spin noise or spin down variations is indistinguishable from a gravitational wave background. So just considering a single pulsar on its own. So really that means that we should actually hope to have degeneracy between those two noise processes. All other signals that you have some frequency dependence or only applied to some subset of the data or have some deterministic waveform are potential pollutants to a gravitational wave background signal. So we try and do our best to charge all of those other signals to as many bins as is necessary before we do our gravitational wave background analysis. The way we evaluate this in terms of the noise models is that if the noise models are sufficient, then there should be no excess noise present in the data after we subtract away time domain realizations of those stochastic and deterministic processes. So this means that at the end of the day, the residuals should be spectrally white and Gaussian distributed. So there's no more red noise present in the data after we subtract off any of the noise processes we've been studying. So of course, in the gravitational wave background search, we do this all jointly in a Bayesian fit with the gravitational wave background terms, so that we're not simply subtracting away all noise straight off the bat. To give you a brief rundown of the noise terms, I'm not going to go into too much detail here, but we do apply a basic noise model to each pulsar, which accounts for variations in the white noise, including multiple E-core parameters across the new ultra-wideband receiver that we use for Parkes. We also include achromatic red noise, which could either be a spin noise for the pulsar or gravitational wave background, and DM variations induced by the interstellar medium and also the solar wind. We also include, for some pulsars, depending on the search outcomes for the noise processes, we include advanced stochastic terms, which only apply to subsets of the data or have specific frequency dependence. For example, scattering noise is one example of that. We also include deterministic terms in a noise model, which deterministic meaning that they can be described in the time domain by an analytic function. Unlike a few other groups, we do not use DMX in our analysis. So all of our DM variations are characterized using a Gaussian process with a power law model. So in terms of the timing residuals, this is what we see straight off the bat. As I mentioned, we don't use DMX, so we're not subtracting DM per epoch. So the predominant thing that we're seeing here in these timing residuals is dispersion measure variations inducing the signal in these timing residuals. So the three colors here are times of arrival measured at 40 centimeters, 20 centimeters, and 10 centimeters. And you can see the dominant source of noise is frequency or wavelength dependent fluctuations, and this is predominantly from DM variations. But there are many other sources of noise in here, which we do our best to characterize as well. So here I'm just showing a subset of timing residuals from a subset of the pulsars in the third data release. I won't go into too much detail about specifically how we develop the noise models. You can ask me that at the end. But after subtracting away the time domain realizations of the noise models, as well as the timing models, of course, we see that our residuals are all pass tests for spectral whiteness and Gaussian distributions. So here I'm showing after subtracting away all the noise models we've developed, everything is looking spectrally white and Gaussian. So that means that our noise modeling has done the job that we set out to do in terms of describing the signals present in the data. So to highlight a few results from this, here I'm showing the marginal posteriors on the amplitude and spectral index of DM variations for 27 of the pulsars, of the 31 that were subject to noise modeling, of which we detect significant DM variations. So the spectral index the spectral indices all seem to be clustered around a value of around 8/3, which is indicated by the dashed line there. And this is what we expect from our Kolmogorov turbulence in the interstellar medium. So it's quite heartening to see that after our advanced noise modeling, we're retrieving results for individual pulsars that are actually consistent with physical expectations. So that really gives us some confidence in the noise modeling that it's doing the job it's meant to do. Moving on to red noise posteriors. So this is basically the achromatic red noise, the red noise in the pulsars that has no dependence on frequency, on radio frequency. And once again, I'm showing the marginal posteriors on the amplitude and spectral index. We see two of the pulsars have particularly loud and steep red noise. These are J1824 minus 2452A, which is in a globular cluster and is likely subject to complex gravitational interactions, and also the well-known J1939 or B1937, which has been known to exhibit steep and loud timing noise for some time now. We also recover shallow and loud timing noise in 1643 and 0711. Two interesting things, though, to highlight are that the majority of pulsars for which we detect red noise are clustered around this region of parameter space, and this is the region from which our common red noise will basically be. That defines the region of parameter space where the common noise can be found. The other really interesting thing I wanted to note here was this black line, which belongs to J1713 plus 0747. So this is one of the most precisely timed pulsars, not just for the PPTA, but also among other groups as well. And in our analysis, we find that the red noise in this particular pulsar is much lower than the plurality of all other pulsars and is inconsistent with this cluster that defines where the common noise should be found. So I'll talk a bit more about that in a bit. Just to highlight some of the common noise results that we found after we've successfully characterized the noise in individual pulsars, we can extract that common noise that I mentioned, and it is indeed pulled out from that region of parameter space where there was a clustering of red noise for individual pulsars. So we recover a common red noise with a log amplitude of -14.5 and best fit spectral index of 3.87. And it seems to not depend too strongly on the choice of solar system ephemeris, which is heartening to see because we know that this was a significant issue in previous data sets. At a fixed spectral index of 13/3 corresponding to supermassive black hole binaries in circular orbits, we recover a strain amplitude of roughly 2 × 10⁻15. So we can ask which of the pulsars in our data set show the most consistency and the most support for this common spectrum process that we can recover. So very roughly speaking, the orange points here are showing consistency. The blue points are showing a measure of support. And we can see that once again, a plurality of pulsars are showing consistency with and support for this common spectrum process. So that's heartening to see. The interesting thing is at the other end of this sort of spectrum, we see that there are 3 pulsars with substantial inconsistency with the recovered common spectrum process, in particular J1713 plus 0747, which I highlighted earlier. And you could see it in that parameter space for the red noise estimates, and we see it here now as well.
3 minutes left.
Okay, thank you. So what's going on? The short answer is we're not totally sure. But however, it's always a good idea to inspect the timing residuals very closely. In the timing residuals on the top panel, we're just showing the residuals before doing any noise modeling. And just inspecting those, we can see there's excess noise at 40 centimeter wavelengths indicated by the red. But really not much there to work with in the green and the blue points representing TOAs from 20 and 10 centimeter wavelengths. So the second panel here is showing what we find after subtracting dispersion measure variations. And really you can see there's not much red noise there to work with. Oops. So we see there's some small degree of high fluctuation frequency noise that's visible by eye. But really the headline is that the signal present in this pulsar is inconsistent with the recovered common red noise that I just highlighted at the 99.8% level. Something else that I thought I'd highlight in this particular talk is the fact that when we conduct our gravitational wave background searches and we look for a common spectrum process, we note that previous results from our group showed that the upper limits in the past were below the level of the signal that we're now seeing in the data. So we decided to revisit that through through a consistent analysis using the same techniques and assumptions and priors. And we basically did that by slicing the data into slices of 6 and 9 years, and then moving those slices along by 1 year at a time and recovering the inferred common spectrum amplitude. So here in the bottom panel, in the 9-year slices, the first 9-year slice and the last 9-year slice are completely independent because our data set is 18 years long. So in the first half of our data, we recover an upper limit of less than 1.2 × 10⁻15. And the last slice there is more consistent with the signal we recover from the full data set, which is indicated by the black band. So once again, the earliest slice of our data shows a signal that is inconsistent with the signal we recover in the full data set. So we're not totally sure of the cause of this. It could be non-stationary gravitational waves or pulsar noise, could be non-power law noise or other misspecification. But somewhere there's an assumption that's being broken, and we're working on where that is. Just to finish up, I thought I'd highlight the influence that our detailed noise modeling has on common red noise estimates. And this is important because a lot of the astrophysics we derive from the gravitational wave background comes from the spectral index you infer from the common red noise. So the orange here shows an analysis of the common red noise using a very lightweight noise model, just employing red and DM noise. The blue is showing what we recover with our full noise analysis. And you can see these contours are at 1, 2, and 3 sigma respectively. So they're substantially in tension with one another. It's also interesting that our advanced noise model recovers a signal that's more consistent with 13 thirds, but we're currently conducting simulations to work out how exactly exactly the noise modeling influences the recovered spectral index of the common red noise.
The time is up.
So I'll finish there and leave up my conclusions. Thank you very much.
Okay, thank you very much, Andrew. Okay, there's one question in the Q&A. So can you describe how you decide what noise models you include for each pulsar?
Yeah, I can. So the basic process, it's an iterative one, and maybe I'll just flick through to this slide here. This is basically a simple flow chart that describes our process. We start with our times of arrival, and we include both historical noise models that were found for those pulsars in the past, as well as the basic noise models that we employ by default. And we basically inspect the residuals to test whether they are residuals after subtracting away the noise and the timing model, whether the residuals are white and Gaussian. If they are, then we're good. If not, then we need to update the noise models. And the way that we decide whether to include certain noise models is simply with a sort of Savage-Dickey Bayes factor analysis. So we add new noise models into the mix. We inspect the corner plots and the marginal posteriors. And if the noise model is significant, then we keep that in the noise model. And then we go through this process over and over until we are satisfied that the noise models are complete in terms of describing the signals in the data.
Okay. So any other questions? So, yeah, okay. There's another question in Q&A. How many noise parameters do you have per pulsar?
That's a good question. It does vary. So some of the pulsars, particularly the new ones that we've been observing. So for the last 3 years, we've observed a set of new pulsars because we've been basically we've got more observing efficiency with the ultra wideband receiver. Those pulsars basically just have the red noise, the DM noise, and white noise. For some other pulsars like J0437, which is very bright and has very complex noise, we need to include very many noise model terms to fully account for the signals there. So it does vary, but you can look at the noise modeling paper to get a sense. Overall, in our gravitational wave background, full gravitational wave background analysis, we have about 260 parameters across our 30 pulsars in that set. But here's just a table showing some of the key noise parameters per pulsar.
Okay, so you have 2 more questions. One is, do you include the gravitational wave background in the model when finding the noise models?
Deliberately not. So when we're developing the noise model, we are developing our null hypothesis for the gravitational wave background. However, once we develop the noise models, that's what we employ as we employ those terms in the gravitational wave background search. So once we've developed the noise models, all those extra noise parameters are modeled jointly. And the idea is that only, basically millisecond pulsar spin noise, that should be the only noise term that is degenerate with the gravitational wave background and should be able to donate power to or donate its support to gravitational waves. So we don't include it deliberately when we're developing the noise models because we are doing a search for gravitational wave background.
And then how do you prevent overfitting the data?
Yeah, so if we're overfitting, once again, we're doing this in a Bayesian way. So we're doing this, all noise models are jointly analyzed. But the other key thing that we assess is that our spectra, our residuals are spectrally white. So if they are being overfit, then they would be over-whitened, and we don't see evidence of that. But more or less, the Bayesian framework, which we do our noise modeling, helps to prevent overfitting.
Okay, thank you. So the last question is, the PPTA dataset with advanced noise modeling shows low base factor for the evidence for gravitational wave background, while the other PTA dataset with basic noise modeling show higher base factor for gravitational wave background. What should we take away from this?
Yeah, I mean, like I said, we're most interested in developing a robust null hypothesis. If we know that, for example, in 1713, if we don't include things like a band noise term to describe the excess noise at low frequencies, that noise gets charged to the achromatic red noise of the pulsar, and that noise gets charged to the achromatic red noise of the pulsar, and basically from there it can contribute to the gravitational wave background signal. So I'd actually argue that doing the advanced noise modeling is how we, things like band noise and scattering noise and so on are not the gravitational wave background. And so we know that by accounting for them properly, we are only including the signal that might be the gravitational wave background in our gravitational wave background model. So the fact that we're not as sensitive, that we have less significant results, may have something to do with the extra noise terms we have, but my hunch is more on just the lower number of pulsars that we have in our data set.
Okay, the very last question. So, yeah, we are over time, but anyway. So how do you define over-whitened?
Basically, if the lowest frequency bin, when we look at the power spectral density, the lowest frequency bins in over-whitened, when things are over-whitened, is well, it's below the level of the white noise, basically. So you have a positive spectral slope at the lowest frequency bins when you subtract away the time domain realizations of the noise models. So in those cases, it's over-whitened, and that's when we would have concerns. But we've seen that, yeah, I'll finish that.
Yeah, thank you very much for wonderful talk and also a lively discussion. So let's move on. Yeah, let's thank Andrew again, and let's move on to the next talk by Paul Baker. Okay, comparison of recent pulsar timing array results. So please go ahead.
So I am Paul Baker, and I'm going to talk about a project in the International Pulsar Timing Array Gravitational Wave Analysis Working Group. And we are comparing the results of the three, I guess, 4 IPTA members that they published recently. So first of all, the working group contains many people, and the IPTA as a whole contains even more people. So this is a list of folks who have contributed to this work, and I'm not going to be able to call out everybody individually with what they did, but we're all here, and a lot of people's time and thought went into this. So the first thing is that the 3 papers we're talking about are the joint EPTA plus NPTA, the Nanograv, and the PPTA papers. And if we look at each of their analysis for a Hellings and Downs correlated process, we get something that looks relatively the same, and we'll come back to this plot later, but with differing significance. So these 3 data sets we're going to be talking about are 3 results. The first one from EPTA plus NPTA is what was called in their paper the EPTA DR2 new plus, which contains about 10.3 years of EPTA data on 25 pulsars, and then 3 years from NPTA on 10 pulsars, which are overlapping. So a total of 25 pulsars for about 11 years when you get the overlap. And the result is that the Bayes factor for a Hellings and Downs correlated background over a common uncorrelated red noise is about 65. The full EPTA data set contains additional time on those 25 pulsars using what they called legacy observing systems that they didn't trust as much and had for various reasons. And so that data was excluded from this particular result they quoted. Nanograv, 15-year data set, used about 15 years of data and contained 67 pulsars. Not all 67 had 15 years of data. There are many with significantly shorter than that, but the longest time spans in the data set are about 15 years. And the Bayes factor reported there for Hellingsdowns over common uncorrelated noise was about 200. And then we just heard about the Parkes PTA's data release 3, which contains about 18 years of data on 30 pulsars that were used in the gravitational wave background analysis. And the Bayes factor there for Hellingsdowns over the common uncorrelated red noise was about 1.5. So that is not strong evidence for or against the Hellingsdowns there. So who observes which pulsars? So this is a kind of a Venn diagram that was made by Paul Ray that shows the pulsars observed by each PTA. So there is a good deal of overlap amongst them. So the EPTA, the EPTA's 25 pulsars, right? Only 3 of them are exclusively timed by the EPTA. Parkes is significantly further south than the other PTAs and has access to the southern sky, so they can see several pulsars that no one else can, but then misses several pulsars that are far north. So all 3 of the power law fits to the Hellingsdowns correlated background agree pretty much by eye. So if we just look at the sort of overlap of the contours, these are showing 1, 2, and 3 sigma contours. It's sort of hard to tell what the heck is going on, but they're all broadly in the same place. Another analysis that was done by all 3 PTAs is a free spectral analysis where you fit, instead of assuming a power law on the common noise, you fit the power in each individual frequency bin. The different PTAs have different frequency bins because they have different observing times. And so the lowest frequency is always 1 over the observing time. So Parkes with 1 on 18 years is the lowest frequency here, and the EPTA with 1 on something like 11 years is their Nanograv here. But again, they all sort of follow the same broad power law in the lowest frequency part of the spectrum. And the black dots here are showing the joint posterior from combining the 3 reported posteriors, and then that value is plotted as a dashed line over there. So if we want to characterize the difference between the different PTAs, we can do so using what was called the tensiometer posterior comparison method from a paper by Ravary and Du in 2021, which was comparing cosmology parameters from the cosmic microwave background, but the same statistical technique works just fine. The basic idea is you can draw a sample from one of those posteriors, then draw a sample from a second posterior, take the difference, and that gives you a single point, in the difference distribution, and then you can continue doing that to map out the difference distribution and integrate to figure out how much tension there is with the difference and 0. So here is the EPTA compared to Nanograv, and the difference distribution is shown, and 0 is the axes shown. And so the difference using a Gaussian equivalent sigma is about 0.76 sigma. The maximum difference is the difference between EPTA and PPTA, or EPTA plus NPTA and PPTA, which is about 1.6 sigma, and Nanograv and PPTA agree at about 0.9 sigma of difference. So one thing is that the power law parameters depend pretty significantly on modeling choices and data choices. So for instance, Nanograv use use the DMX dispersion measure variation models. The other PTAs use a DMGP, and even there was a nanograv analysis using DMGP that significantly shifted the recovered power law parameters. There could be different priors on some of the same model parameters. So the PPTA use slightly different priors than nanograv and EPTA. Whether or not you include legacy data, so EPTA's legacy data was excluded for this. If you include it, you get different parameters. And again, the different observation times lead to different Fourier bases. And we also, as you heard earlier today, the EPTA chooses the number of basis coefficients to use for each pulsar one at a time, basically. So they have different numbers of Fourier coefficients for each of their pulsars, where the other PTAs have roughly the same number for everything. So in that sense, the various posteriors we might not trust as much as maybe we should. We've heard a lot about advanced noise modeling and how these modeling choices can affect the posteriors. But if we just take the 3 posteriors at face value and do something like a logical and take the product of the 3 distributions, you get the joint distribution, which is shown in black here. And so that is the joint distribution that was plotted previously. It gets narrower, right, when you're combining information from multiple experiments. But I'm not, I guess I would take this with a little grain of salt. If you want to make astrophysical inference based on these 2 parameters, then again, there's a lot of modeling choices that go into this. So I think waiting for better spectral characterization is probably a good thing. All right, so we talked about, does the background agree? Does the Hellingsdowns correlated power law agree using the MCMC chains that were published in the actual analyses? We can also do the same with the intrinsic pulsar noise parameters. So using those same MCMC chains from those same runs, we can look at the posteriors on the noise parameters, and in the same way, calculate the difference between the noise parameters. So if we look at EPTA plus NPTA compared to nanograv, one thing is EPTA, NPTA did not use the intrinsic red noise model for all of their pulsars. They only used it when it was significant in their background run. And so that's why there's only a handful of pulsars here where the EPTA used red noise compared to nanograv. And there is a pretty small distance in a Gaussian equivalent sigma for most of them, and this one pulsar, J1012 plus 53, has a large difference. One thing is that this particular pulsar has a very flat intrinsic red noise spectrum with a low spectral index. So it is close to white noise, it's pretty flat. And because of that, the EPTA chose to use close to 150 Fourier frequencies in modeling it, whereas nanograv used 30 frequencies for everyone. And so the difference here, I think is more of a modeling difference than a real physical difference. By missing a lot of the higher frequency information, that changes, what nanograv sees compared to what the EPTA and NPTA see. And that higher frequency information matters for this pulsar because it has such a flat spectrum. Looking at PPTA compared to nanograv for the intrinsic red noise parameters, most of them again are less than 1 or maybe 2 sigma difference between what nanograv and PPTA see for the intrinsic red noise. 2 are different. J0437 minus 47 has a big difference, and that is a pretty far south pulsar. Nanograv observes it with only the VLA. It can't be seen from their other telescopes. So nanograv has a much shorter time span on that pulsar compared to PPTA. And so the fact that nanograv can't see the red noise sort of makes sense because it doesn't have access to the lowest frequencies that PPTA does with more time span. 1643 is another pulsar that the PPTA sees a big difference in. And that is one of the pulsars that has a much more, complicated model in its dispersion measure variations and other chromatic models compared to nanograv. So it includes an extra high frequency achromatic process, band noise, and scattering noise that nanograv doesn't have. And so that one has a big difference, and some of the other pulsars that have these sort of big modeling differences are the other ones that are close to 2 sigma difference. So 0613, 1713, and 2124, I think, and 1939. So those are the sort of modeling differences, I think, are more important in the differences in the intrinsic red noise. And these are, I should say, right, these are coming from the Hellingsdowns correlated analysis. So
3
these
minutes
runs
left.
3 minutes.
Yes.
Okay, I'll skip ahead and we'll look at EPTA in PTA. Similar thing versus PPTA, similar thing. There are modeling differences. There are some other differences here because both the PTAs model dispersion measure variations using a Gaussian process. We can look at those differences as well. That's where all the differences live. And I think a lot of it is going to come down to in PTA's very low radio frequency coverage compared to PPTA. So again, I think the differences are understandable. So one other analysis we can do is what's called a factorized likelihood, where you take single pulsar noise runs or single pulsar analyses and then put them together after the fact to get a common uncorrelated red noise posterior. So the gray curves are all the single pulsars amplitude posterior for this log 10 common uncorrelated red noise amplitude. When you put them all together, you get the blue curve. And then we can do the same for all the PTAs. And you can also mix and match pulsars if you want. So you could take the 25 ePTA pulsars, and it's not shown, but we could grab some nanograv or PPTA pulsars that the ePTA doesn't time and mix them in with the ePTA pulsars. One thing you can do with these common uncorrelated red noise posteriors is use the optimal statistic to calculate the signal to noise for the correlations. So these distributions come from this factorized likelihood analysis, and this factorized likelihood analysis didn't come from the PTA's runs. They were new runs where the same Fourier basis was used for all the PTAs and the same noise models were used for all of the PTAs. So the final thing is that if we start with, say, ePTA plus NPTA here, we have these 25 pulsars, and then we could add in the factorized likelihood way, these other pulsars that nanograv times that PPTA doesn't. And then we could pick up the 13 remaining pulsars from PPTA and add them in and get a common uncorrelated red noise posterior using E plus N plus nano plus Parks. And then do the optimal statistic to get a signal to noise ratio from the optimal statistic, which are shown in these box and whisker plots. So this is the ePTA in PTA alone. This is adding the nanograv, then the Parks. This is the other order where you start here, add the PPTA in, and then the remaining nanograv. So you could do the same starting with the nanograv, add in E plus N, then add the Parks, or add in the Parks first, then E plus N, or starting with Parks only and adding E plus N plus nano, or the opposite direction. So in all cases, by combining pulsars in this using the optimal statistic, you're getting more pulsars by adding more pulsars in, and so you should be able to see the correlations better. And so in all cases, adding extra pulsars is increasing the signal to noise of the Hellingsdowns correlations. I should clarify, this SNR is not a sigma significance for a detection because the background distributions are not Gaussian. So, right, the nanograv alone was about SNR 5, but that was not a 5 sigma detection. So to conclude, IPTA DR3, when we combine everything that we've seen so far, there will additionally be pulsars timed by Meerkat African PTA. And so there'll be 115 pulsars total, and you can learn more about that from Quo tomorrow in a talk there. And Ghulam gave a talk earlier today on the IPTA, which I believe was recorded, so you could also see more of that. Thanks.
Okay, thank you very much. Any questions, please? Oh, yes. Is there a reason to go for the logical and of the posteriors from different data sets as opposed to the union, their union?
Yeah, so this is the I guess the intersection. And so going with a union, the sort of standard thing to do is to use an intersection to say and. We have 3 experiments. We want to say this experiment and that. I think it might be, if we did do a union, right, it would basically just be a wider posterior that goes from sort of the blue edge over to the green edge. So it would just sort of, this sort of shows by combining experiments, we should get a better measurement of something, but I'm not sure I trust any of the 3 measurements. So take that with what you will.
Thank you. So the next question, how is it possible that PPTA versus nanograv for J1713 is only about 2 sigma difference, when in the previous talk we've heard that J1713 has basically no Rn in PPTA?
So this is the red noise that's left over after getting the common process. So we're taking the analysis that looks for Hellings and Downs correlated background and individual pulsar noise simultaneously. And so when you do that, the difference here is, so I assume what I would guess, without looking at it in front of me, I would guess the PPTA 1713 is going to be kind of an upper limit looking thing like we saw in the nanograv. The remaining red noise in 1713 will overlap with that a little bit wherever it lies after it's fitting for the background. So that is the difference of the intrinsic red noise after fitting for the background.
Okay, the last question, how difficult would it be to analyze the full data set from PTAs in the unified pulsar model?
So to do the IPTA DR3, I'm guessing, is that the question? It's a lot more complicated than you would guess, because the combining of the data is tricky. So you have to refit the pulsar timing models, which is something of an art. And so it just takes a lot of time. It takes a lot of person power. And so if you talk, in Quo's talk, I believe there are something like 20 of these 115 pulsars are done, and the tools being put together to do those 20 are going to make the remaining 95 easier. But it's just going to take time to get the full data set going, and then it will take time to analyze it. So, yeah.
So is there any political issue about that? Or only technical difficulties?
It's just technical difficulty. So
okay, good.
All of the members of the IPTA who are like full members of the IPTA have already given their data to the combination group who's working on it. So there's nothing like, the main way to join the IPTA is to join the data sharing agreement.
Okay, thank you very much. So time is up. So let us thank Paul again and close this session. So this concludes the last session of the day.
Yeah, I was going to say thank you very much, Junichi. Yeah, and our next session will start in about 6 hours. So hopefully we'll see some of you then. Take care, everyone.
Okay, see you then.